Kepler's law. Planetary motion had been observed by the astronomers since ancient times. Before Galileo, all observations of planets' position were made with the naked eyes. Obviously, after Galileo, the telescopes were available. Hence, the observations could be made more accurately and more precisely. By the 16th century, a lot of data were available about planetary positions and motions. Johannes Kepler studied this data. He noticed that motion of the planets follows certain laws. He stated 3 laws describing planetary motion, and these laws are known as Kepler's laws, which are given below. Now, Kepler couldn't explain the reason behind these planetary motions. He only observed the motions, and then from that he deduced the laws mathematically. So the first law states that orbit of a planet is an ellipse with sun at one of the foci. Now, before going into details of this law, we should understand what is an ellipse. An ellipse is a curve obtained when a cone is cut by an inclined plane. So here, as you can see, a cone is shown. If the cone is cut by a plane which is horizontal to its base, you will get a circle. But as you can see it here, if the cone is cut by an inclined plane, that means by a plane which is making an angle with the base, then you will get such type of diagram, and that will be called an ellipse. The special property of ellipse is such that there are 2 points F1 and F2 inside the ellipse, such that the distances of these 2 points from any point on the ellipse, when added up, gives you a constant value. For example, A is a point on ellipse, so you can add the distances AF1 plus AF2, where F1 and F2 are the 2 foci of the ellipse and A is any point on the ellipse. Then this addition will be equal to BF1 plus BF2. That means B is another point on the ellipse, BF1 and BF2, and that will be again equal to CF1 plus CF2, where again C is another point on the ellipse. So addition of distances of any point on the ellipse from the foci is always equal. So this is the property of the ellipse. Now again look at this law. Orbit of a planet around the sun is an ellipse with sun as one of the foci. So this sun is at, let us say, point F2, and again there is point F1 where nothing is there. Sun is at the focus and the planet is revolving in an elliptical direction, elliptical orbit around the sun. Kepler's second law states that the line joining the planet and the sun sweeps equal areas in equal intervals of time. That means if the planet takes time t to go from A to B, again same time t to go from C to D, and same time t to go from E to F, then area swept by the planet, that means area ASB, will be equal to area CSD and that will be equal to area ESF. All the areas will be equal if the planet is taking same time to go from one point to the other. So other meaning of this statement is that the planet will move faster when it is nearer to the sun and planet will move slower when it is away from the sun. The planet will move faster when it is nearer to the sun and slower when it is away from the sun. That means it will cover more distance in given time when it is nearer to the sun, and it will cover lesser distance in given time when it is away from the sun. All this figure can be approximated as the triangles, and then you can see that for this triangle ASB, this is the base and this is the height. So if height is less, base is more. Here you can see height is more, so base is less, so that the area it remains same. So this is Kepler's second law of motion. Line joining the planet and the sun sweeps equal areas in equal time interval. Kepler's third law says that square of the period of revolution around the sun is directly proportional to the cube of the mean distance of the planet from the sun. So it is little bit complicated to digest at the first sight. What is the period of revolution of the planet? Period of revolution of the planet is nothing but the time taken by the planet to complete one revolution around the sun. So that is actually 1 year of that planet. 1 year of that planet. Just as Earth has 365 days in a year. That means Earth takes 365 days to complete one revolution around the sun. So this period of revolution T and its square is directly proportional to cube of the mean distance of the planet from the sun, that is r cube. What is r over here? If this distance between the sun and the planet, here it is r1, here it is r2, then r3, r4, r5, r6, there will be infinite set distances. If we find the average distance and if we find the cube of that average distance, then we can say that t square is proportional to r cube. That means the square of period of revolution around the sun is directly proportional to the cube of mean distance of the planet from the sun. That means the ratio t square upon r cube is a constant over here. Kepler obtained these laws simply from the study of positions of planets obtained by regular observation. He didn't know physics behind these motions, but it helped Newton in the formation of his theory of gravitation. So what are the three laws? We'll just quickly revise them. First law says that orbit of a planet is an ellipse with the sun at one of the foci. Second law says line joining the planet and the sun sweeps equal areas in equal intervals of time. And the third law says square of its period of revolution around the sun is directly proportional to the cube of the mean distance of the planet from the sun. So these laws were purely observational laws, but it helped Newton to formulate his universal law of gravitation. So what is Newton's universal law of gravitation? According to this theory, every object in the universe attracts every other object with a definite force which is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. Again, at the first sight, law looks little bit complicated. So first, now let us look at its mathematical form. So figure 1 shows this 1.45 shows two objects M1 and M2. These are two masses M1 and M2, and they are kept at a distance d from each other. Then the law says that the force of attraction, the gravitational force of attraction between these two objects is proportional to the product of masses, that is, it is proportional to m1 multiplied by m2. And the second statement tells us that this force is inversely proportional to the square of the distance between them. So if we combine the two statements together, we have F is proportional to m1 multiplied by m2 divided by d square, and if the proportionality sign is to be converted into equality sign, we have to take a constant of proportionality and we take it as capital G. So F equal to capital G m1 multiplied by m2 divided by d square. This is the mathematical form of Newton's law of gravitation. Now, having seen this mathematical form, again go back to statement. Every object in the universe attracts every other object. So every object means m1, every other object means m2, attracts each other with a definite force which is F. This force is directly proportional to the product of the masses. So here it is m1 multiplied by m2 and is inversely proportional to the square of the distance between them. So it is 1 upon d square. So if we remember the mathematical form of Newton's universal law of gravitation, then its statement can be easily written from that law. Now here this capital G, we have taken it as constant of proportionality. So when equality sign is introduced there, constant of proportionality comes, and that constant of proportionality is called Newton's universal gravitational constant. It is called universal gravitational constant. Henry Cavendish was the scientist who first calculated the numerical value of capital G. So how did he find? We have the formula F is equal to capital G m1 m2 upon d square. If we readjust the terms, if we transpose this d square here, so that will give you capital G is equal to, we transpose the d square over here, so it will be in multiplication m1 m2, here it is in multiplication, after transposition it will go into the division. So G is equal to Fd square upon m1 m2. Now if there are two masses of 1 kg each, that means m1 equal to 1 kg, m2 equal to 1 kg, and we keep them at a distance 1 meter from each other, then d is also equal to 1 meter. So if in this we put F into 1 square divided by 1 into 1, that will give us G is equal to F. So we can say that the value of gravitational constant is the force of attraction between two unit masses, that means masses of 1 kg, kept at a unit distance away from each other. And if we want to find the SI unit of this capital G, we know that unit of force is Newton, unit of distance is meter, so square is there, so meter square, unit of m1 mg is kg, so kg into kg is kg square. So value of G found by Henry Cavendish is 6.673 into 10 raised to minus 11 Newton meter square per kg square, or we can write Newton meter square kg raised to minus 2. These two are one and the same. So this is how the unit of capital G is found, and its value was found experimentally. Now if we look at this law once again, we see that if mass of one of the object is doubled, that means out of m1 m2, if one thing is doubled, then the entire force will be doubled. Also, if the distance between the two is double, that means if this 2d means d is doubled to 2d, then what will happen? We will have F is equal to m1 m2 and 2d square is 4d square. So it will be equal to 1 by 4 into m1 m2 upon d square. So the force will become 1/4 if the distance is doubled, and the force will become double if one of the masses is doubled. Now to find the distance, we make use of center of mass of the given masses. If the given masses are spherical in shape, then the center of the sphere acts as the center of mass. If the given objects have uniform density and they are symmetrical objects, then their centroid acts as center of mass. Otherwise, the center of mass experimentally found can be taken to measure the distance between the two objects. Now let us understand how Newton used this Kepler's third law to formulate his law of gravitation. For that, we have to consider the uniform circular motion of the planet around the sun. So we approximate the elliptical motion into circular motion, and we say that an object is moving in a circle with a constant speed. We have seen earlier that such a motion is possible only when there is a centripetal force acting on the object. That means there must be a force directed towards the center of the circular path, which is continuously changing the direction of that object, direction of motion of that object. So a center seeking force or a force acting towards the center of the circular path is necessary for continuation of the circular motion. Now it can be proved that its value is equal to F is equal to mv square upon r. Now we take this value without mathematical proof, because the proof is beyond the scope of our syllabus. So just remember F is equal to mv square upon r, where m is the mass of the planet which is revolving, v is the speed of the planet, and r is the radius of its orbit around the sun. F is the force which is necessary for continuation of the circular motion. So remember the formula, F is equal to mv square upon r. If a planet is revolving around the sun in a circular orbit in uniform circular motion, then there is a centripetal force acting on the planet which is necessary for the continuation of circular motion, and this force is F equal to mv square upon r. Now let us consider that a planet is revolving in a circular orbit around the sun. So this is sun, this is the circular orbit in which the planet is revolving, this is planet. Then in one revolution, how much distance the planet will cover? The planet will cover a distance equal to circumference of the orbit. So speed can be found by the formula distance travelled upon time taken. So in one complete revolution, distance travelled by the planet is equal to circumference of the orbit, which is equal to 2 pi r, where r is the radius of the orbit. And if the time taken for that is capital T, that means capital T is 1 year of that planet, then we can say that v, speed equal to distance 2 pi r upon time capital T. Now if we put this value of v in the equation, F is equal to mv square upon r, what we will get? We will get F is equal to m as it is, v square, that means 2 pi r upon t bracket square divided by r, like this. So if we square this term, you will get m, then 2 square is 4, pi square is pi square, r square is r, divided by t square is t square, and there is 1 r in the denominator. So 1 r will be cancelled, and we will get F equal to 4m pi square r upon t square, 4m pi square r upon t square. Now if we multiply this by r square divided by r square, now r square divided by r square is nothing but 1. So if we multiply a fraction by same number in the numerator and the denominator, value of fraction will not change. So if we multiply and divide by r square, then what we will get? Then we will get f is equal to, as it is 4 pi m, everything is constant, 4 pi square into m. Then this one r is there and we are multiplying it by another r square. So r into r square. So it will be r cube over here divided by t square into this r square will be there, r square. Now look at this fraction r cube upon t square, and this is very specific fraction. Kepler's third law tells us that t square upon r cube is a constant. So if t square upon r cube is a constant, r cube upon t square, that is the reciprocal of a constant, will also be a constant. 4 is a constant, then pi is a constant, mass of planet will remain constant. So we get f is a constant multiplied by a constant multiplied by a constant multiplied by a constant. So everything is constant upon r square. And that gives us that f is inversely proportional to r square. Thus Newton concluded that the centripetal force, which is the force acting on the planet and is responsible for its circular motion, must be inversely proportional to the square of the distance between the planet and the sun. Newton identified this force with the force of gravity and hence postulated inverse square law of gravitation. So force is inversely proportional to the square of the distance. This part of the statement comes from this derivation, which makes use of Kepler's third law of planetary motion. Hence the gravitational force was defined, and it was possible to explain the motions of the planets, stars and other constituents of the universe from this law. This law is very weak, so we cannot experience the force of gravitation between two small objects on the surface of the earth. But when huge masses are considered, this law can explain